In this video, we're going to be using conservation of angular momentum to solve an example problem. The example problem I'm going to solve is closely based on a demo which I showed in the previous video. So if you have not already watched the previous video, I would encourage you to go back and watch the previous video and then join this video. Here's the example problem. We have a tray in the shape of a cylinder which is rotating about an axis through its center. The angular velocity of that tray is omega initial. The radius of the tray is r, and the mass of the tray is m sub t. We are given mass of tray is 300 grams, initial angular velocity 6 radians per second, and the radius of the tray 15 centimeters. Then, with the tray rotating, suddenly I drop some heavy jar at some point on the tray, which is a distance little r from the center of the tray. The mass of the jar is m sub j, 500 grams. That distance little r between the center of the tray and the point where I place the jar is 10 centimeters. As we saw in the previous video, when I place that jar onto the rotating tray, the angular velocity of the rotating tray substantially decreases almost immediately. So we're going to say here that the angular velocity of the rotating tray and jar together, after I have placed down the jar, is omega final. We're going to use conservation of angular momentum to find this final angular velocity. As a quick refresher, conservation of angular momentum says that if you have a group of objects and no outside torques act on that group of objects, then the total angular momentum of that group is constant. So if we have a process where no outside torques act, we can say that the total angular momentum at the beginning equals the total angular momentum at the end. To apply conservation of angular momentum, we're going to work out an expression for the total angular momentum in the initial situation, an expression for the total angular momentum in the final situation, and then we're going to equate those expressions. All right, what would be the total angular momentum in the initial situation? In the initial situation, the only thing we have rotating here is the tray itself. So the angular momentum of the tray would be, let's use the formula, moment of inertia of the tray times the angular velocity of the tray, which in that initial situation is omega initial. Now let's come to the final situation. In the final situation, we have the tray rotating at this smaller angular velocity, omega final, but then the jar is rotating around with it at the same angular velocity. So what would be the angular momentum in the final situation? Well, first we would have the angular momentum of the tray itself, which is now equal to moment of inertia of the tray times the final angular velocity. Then we add on the angular momentum of the jar. That would be moment of inertia of the jar times the final angular velocity. You can probably tell that to proceed with this solution, we're going to need to be able to calculate the moment of inertia of the tray and the moment of inertia of the jar. We're going to assume that the tray here is a cylinder, and we can look up the moment of inertia of a cylinder rotating about its own symmetry axis. The moment of inertia for a cylinder rotating around its own symmetry axis is 1/2 the mass of the cylinder, so here, mass of the tray, and then times the square of the radius. So that's the moment of inertia of the tray with respect to rotation around its own center. We also need the moment of inertia of the jar. Let's assume that the jar is much smaller than the tray, and because we're assuming that the jar is much smaller than the tray, we're going to use the formula for the moment of inertia of a point mass. Moment of inertia of a point mass is equal to the mass itself multiplied by the square of the distance between the point mass and the center of rotation. Now, in this problem, that distance is little r, so the moment of inertia of the jar with respect to rotation around the center is the mass of the jar times little r squared. Now let's proceed to using angular momentum conservation. We're going to say total angular momentum in the initial situation equals total angular momentum in the final situation. Total angular momentum in the initial situation is moment of inertia of the tray times initial angular velocity. Total angular momentum in the final situation would be the quantity moment of inertia tray plus moment of inertia jar times final angular velocity. So let's solve for the final angular velocity. We have omega final equals moment of inertia tray times omega initial divided by the quantity moment of inertia tray plus moment of inertia jar. Now let's substitute those expressions for moment of inertia tray and moment of inertia jar. That gives me omega final equals, for moment of inertia tray, 1/2 mass tray big R squared, and omega initial. And in the denominator, 1/2 mass tray big R squared plus mass jar little r squared. To simplify the algebra just a bit, I'm going to multiply top and bottom by 2. That gives me omega final equals mass tray big R squared omega initial divided by mass tray big R squared plus 2 mass jar little r squared. Now let's make our numerical substitution. We have then omega final equals mass tray 300 grams. Now the grams is going to cancel out here, so I don't need to convert to kilograms. So I'll just keep grams as grams. So 300 grams r squared 15 centimeters squared, omega initial 6 radians per second. In the denominator, we have again 300 grams times 15 centimeters squared plus 2, and then mass jar is 500 grams, and little r is 10 centimeters, and that is squared. Let's do a quick unit check. The unit in the numerator is grams centimeters squared times radians per second. In the denominator, both terms have units grams times centimeters squared. So grams cancels grams, centimeters squared cancels centimeters squared. So the unit that remains is radians per second, as we would expect for an angular velocity. So we have something with units of radians per second, and when you put this into your calculator, I believe you will get 2.42 radians per second. So coming back to the initial figures, when we put that jar onto the rotating tray, the angular velocity decreased from 6 radians per second to 2.42 radians per second. Now we have done an example problem using conservation of angular momentum.